Hello everyone. I hope you're doing well and staying safe. This is one of our last couple of lectures on HEMI 2010 material, and the aim for today's lecture is to look at the idea of centroid or center of mass of the body, and solve some problems on this concept. Okay. So aim for today's lecture is look at the concept of centroids. Okay, then we will be looking at this concept from the perspective of a composite shape. Okay, so we will be focusing on centroid of composite bodies, composite shapes. We will be solving a couple of problems on this particular idea for today's lecture. But first of all, we're going to look at some basic definitions of what is a centroid. Okay, so we will define a centroid. So centroids are typically labeled as the geometric centers of bodies. Okay, that's one way of looking at it. Okay, these are the geometric center of bodies or shapes. Okay, then we will also say that if we are on Earth, where the acceleration due to gravity is a constant, and if we consider bodies whose density is going to remain constant, then the definition of a centroid is the same as the definition of a center of mass or a center of gravity. Okay, so the second thing we're going to say is that if acceleration due to gravity is a constant, and if the density of the body is a constant, okay, and if density is a constant of the body is a constant, then we can say that the centroid, centroid is the same as the center of mass is the same as the center of gravity of the body. Okay, this is a key statement here. Okay, centroid the same as the center of mass and is the same as the center of gravity, and this is under the assumption that acceleration due to gravity is a constant and the density of the body is also a constant. Okay, all right. Now we come to the actual definition of these quantities. That's the basic idea that I want to portray here. The definition is the following. Okay, we define centroid as the point on the body or outside the physical description of the body through which the line of action of the weight of the body passes through. Okay, so centroid is defined as the point on the body or outside the physical description of the body, okay, physical shape of the body, through which the line of action of the weight of the body will be passing through. Okay, all right. The key statement here is it should be a point on the body or outside the physical shape of the body through which the line of action of the weight passes through. Okay, and actually this is the definition of the center of mass of the body, but then we are saying that the density of the body is a constant, which implies that we can say that the centroid is the same as the center of mass of the body. Okay, and typically we will be dividing bodies into two types: simple connected shapes and then composite shapes. Okay, so we will be dividing bodies into simple connected shapes, or shapes into simple connected shapes. Okay, so our focus, I mean, let me take a step back. Our focus is to look at the centroids of two-dimensional shapes. Okay, so look at centroids of two-dimensional shapes. Okay, and from that perspective of two-dimensional shapes, we can divide this into two types: simple connected shapes and then composite shapes. Okay, so 2D shapes, 2D shapes can be divided into two types: simple shapes, simple connected shapes, and then composite shapes. Okay, so we will define simple connected shapes. Simple connected shapes are the following: simple connected shapes okay, these are the simplest possible shapes that we know. Okay, these are the basic building blocks. Okay, they are the basic building blocks. And these are the simplest possible shapes we know geometrically. Okay, and if you look at simple connected shapes, the common examples are rectangles, circles, and triangles. Okay, so common examples of simple connected shapes are rectangles, okay. If you look at rectangular shapes, then the centroid is at the center of the shape. This is a no-brainer, right? There's nothing too much think about here. Okay, so if I look at this rectangular shape, a square is a special rectangle, right, with all the sides being equal to each other. So if this is a rectangular shape, then the centroid of that shape is right at its center. Okay, this is the location of the centroid. Okay, let me write that out. This is the location of the centroid. Okay, then we look at other simple shapes, for example a circular shape, so B, circular shape, and then C are triangles. Okay, our aim is typically to focus on rectangular shapes, so I'm not going to look too deep into circular or triangular shapes. Of course, one can obtain the centroids of these shapes by means of basic integration techniques, which we are not going to be looking at. Okay, so our focus is going to be mostly on the rectangular shapes. Okay, so I just want to make a note here. Okay, so note, we can obtain centroids by making use of the idea of integration. Okay, so we can obtain location of centroid of any body using integration. We will not be focusing on this, we will rather be focusing on composite shapes. Okay, so our focus is limited to composite shapes. Okay, all right, so we come to the definition of a composite shape then. Okay, what is a composite shape? Okay, the basic idea is fairly simple. A composite shape is nothing but a combination of two or more simple connected shapes. Okay, a composite shape is a combination is a combination of two or more simple connected shapes. Okay, and just to rewrite this definition again, so a composite shape is a combination of two or more simple connected shapes. Okay, simple connected shapes. Alright, and I just want to box this definition because this is something that we will be looking at quite often. Okay, let me take that and duplicate that and bring it down here. Okay, and complete the boxing. All right, and so the basic idea is, okay, why are we interested in these composite shapes? Okay, this is mostly because of the fact that most of the bodies that we typically study in strength of materials, when we look at the beams, the cross sections of beams, these are made up of composite shapes. Okay, so the reason behind this is the following. Okay, so the reason for focusing on composite shapes is that many of the beam cross sections, a majority of the beam cross sections are made up of composite shapes. Okay, and standard examples of these are beams which have an I cross section, okay, or a T cross section. Okay, so let me draw a couple of these. So this is an example of a beam with let's say a T cross section. Okay, one of the most common cross sections that you will come across, and if you look at the cross section of the beam, of course it's going to be a little more symmetrical than what I've drawn, but you get the basic idea that it looks somewhat like this. Okay, and if I complete the cross section, so here is the basic cross section, and you can immediately see that this beam cross section, which is a T cross section, is made up of two simple rectangular shapes. So this is an example of a T section. Okay, so this is a T section. That's a composite shape. Okay, it's made up of two rectangles. Okay, so that's one example of a beam cross section. We could also have beams that are of a boxed cross section, or an I section, for example. It's one of the most common sections that is used for railway tracks because they are having a good capability to withstand bending stresses. Okay, so for example, if you look at I cross sections, then here is an example of that. Let me just draw a very small quick one. Okay, and I can just copy this, and I'm sorry, I can copy this and bring it down here. Okay, so if I complete the I section, so there will be a piece. The top two portions are called the flange, and the middle piece is the middle section of the I section. Okay, the top and the bottom are the flanges, as you can see here. So this is an example of an I section which you're seeing here. Okay, and completing the figure, essentially, as you can see. Okay, so this is an example of an I section. So in this I section, you're saying that there are actually three simple connected shapes, or three rectangles that can be typically used to construct the I section. Okay, so this is an example of an I section. This is also a composite shape. And other examples are, boxed beams, where you have two rectangular pieces that are inset one inside the other. You could have tubular beams where you have two circular pieces which are combined together. But our focus is mostly going to be on composite shapes that are made up of simple connected rectangles. Okay, this is mostly from the perspective of strength of materials. Okay, so our main focus, let me just rewrite that. Okay, so our focus is look at composite shapes that are made up of two or more simple connected rectangular shapes. Okay, this is the key statement that I want to make here. So composite shapes that we're going to be looking at are made up of two or more simple connected rectangular shapes, and common examples of these are the T sections, the I sections, L sections, C sections, and so on. Okay, so T section, the I section, then you have the L section, C section, etc. Okay, and why do we want the location of the centroid? Is essentially from the point of view of stress and strain analysis. We look at the location of the centroid, then we can see, you will see this in strength of materials, that the centroid essentially distinguishes states of tensile versus compressive stresses if you use simple beam theory. Okay, so very, very basic idea. Okay, why do we need centroid location? Okay, from the perspective of basic strength of materials, from point of view of basic strength of materials, the location of the centroid distinguishes between states of compressive and tensile stresses. Okay, location of centroid distinguishes between states of compressive, let me write that better, versus tensile stresses. Okay, which means that the idea of centroids is very useful for stress analysis. Okay, and the idea of what you'll see in the next lecture is also called as moments of inertia. So the location of the centroid enables us to distinguish between states of tensile versus compressive stresses. I'm not going to go into the details of these things because you'll be seeing this when we talk about a material and strength of materials. Okay, so I'm going to skip all those ideas here. Okay, what we need to know is we need to know how to locate the centroid of composite shapes. That's all we need to know from the perspective of statics. The application is going to come from strength of materials. Okay, so in statics, locate the centroid of composite shapes. Okay, that's the main thing. And then in strength of materials, what you'll be seeing the location of the centroid will be useful for analyzing stress and strain. for analyzing stress and strain. Okay, so that's a distinction here. And what we're going to be doing is we're looking at centroids of composite shapes, as I have mentioned in the previous situations, right? So we're going to come up with a basic formula for that. Okay, so how to locate the centroid of composite shapes. So how to locate centroid of composite shapes. Okay, that's the main aim for today's lecture, and we will be solving a couple of problems on this idea as well. But before that, we need to look at some basic definitions and ideas of these things. Okay, the first step A is to set up an origin and a coordinate frame. Okay, so set up a coordinate frame at some suitable location, and this coordinate frame will be a Cartesian coordinate frame. Okay, obviously Cartesian coordinate, which means that we need to select a suitable origin for this coordinate frame. Okay, so select a suitable origin for the coordinate frame. And choosing this suitable origin is going to be one of the key things you're actually going to be doing. I mean, if you choose a proper origin for the coordinate frame to analyze the problem, then half the battle is won. Okay. Then the second thing is this: we're going to make use of the definition of a centroid. Mathematical definition of a centroid, okay, is the following. Mathematical definition of centroid of a composite shape. Okay, centroid of a composite shape is equal to the area weighted average of the centroid of the simple connected shapes. Okay, and if we make use of a formula, for example, let's take a quick hypothetical example. Okay, and we will of course look at actual numbers for this example as well very soon. Okay, so hypothetical example. Let's say that I have an L-shaped cross section. Okay, so let me draw that out here. So this is my L-shaped cross section, which I'm drawing out here. Okay, how do I find the centroid location for this one? The first step is to set up a coordinate frame. So I set up an origin here. Okay, so this is going to be my origin O. So this is an example of a composite shape, right? I see that there are two rectangular shapes that I can divide this composite shape into. So I divide the composite shape into a minimum number of simple connected shapes. Okay, so that's something that I also do. Okay, I divide the composite shape into a minimum number of simple connected shapes. Right, in this particular example, I can say that, okay, I'm going to divide this into one rectangle here, right? If it's an L-shaped body, then I'm going to have one rectangle here, okay? Then I'm going to have one more rectangle on the top, right? Then I set up a coordinate frame, okay? I set up a coordinate frame with the origin as chosen there. So this is my origin. I call this as the y-axis, then I call this as the x-axis, right? And then here is what I do. I locate the centroid of the individual simple connected shape. So in this case, the centroid of this little rectangular piece, if I shade this out, right, is going to be one rectangular piece here, right? And the centroid of this is going to be located at its geometric center. Okay, let me draw it in the form of a circle. Okay, so that's the centroid of this geometric shape here. Then likewise, I'm going to look at the centroid of the other shape. So here is the centroid of the other shape. Okay, this is going to be shape 1. Okay, and then this I'm going to call as shape 2. The location of the centroid of shape 2, I'm going to be calling that as the following. Okay, that is C2, which is going to be labeled as x2 bar, y2 bar, and I'll tell you what x2 bar and y2 bar mean. Okay, and then the location of that point is going to be C1, which is x1 bar, y1 bar. Typically the bar implies that this is the location of the center of mass, and then we can find the center of mass of the composite shape in the following way. Okay, so the first thing, let me actually rewrite this in the form of a couple of steps. Okay, so let me say the following. So first thing is divide the composite shape into a minimum number of simple connected shapes. Okay, that's an important thing. So divide the composite shape into a minimum number of simple connected shapes. That's the first thing. The second thing is choose a suitable origin. And then locate the centroid of the simple shapes with respect to this origin. Okay, locate centroid of the simple shapes with respect to this origin. In this case, we have the origin as the point O here, and this is in our example, this is called as location C1, which is x1 bar, y1 bar, and location C2 is x2 bar, y2 bar. Okay, and then the third step is the following. Okay, third step is x bar is the location of the centroid, the x location of the centroid, you can say that, okay, if you want. Okay, so this is the x location of centroid of the simple shape of the composite body of composite. And if y bar is the y location of the centroid of the composite shape, this is based on the origin you have selected. Okay, that is an important thing. This is based on selected origin. Okay, let me write that properly. Okay, so selected origin and if I say that the area of this shape is A1, okay, and the area of this shape is A2, then I have the following. Okay, if so, area of the simple connected shape 1 is A1, area of simple connected shape 2 is A2, then we can say the following. Okay, then x bar is going to be x1 bar A1, x2 bar A2. Okay, this is let me write the generalized formula first. Okay, so the general formula is the following. Okay, general formula, let me write that out. Okay, general formula, the area weighted average of the individual shapes. Okay, so that's going to be x bar is equal to summation, okay, I going from 1 to n, which means that the number of composite bodies, this is going to be xi bar ai, all of this divided by summation I going from 1 to n, once again ai, and then y bar is going to be likewise, okay, summation I going from 1 to n yi bar ai divided by summation I is equal to 1 to n ai. Okay, and then for the hypothetical example, here is what we get. Okay, if I look at the hypothetical example, then x bar is x1 bar a1, x2 bar a2, all of this divided by a1 plus a2, and y bar is y1 bar a1, y2 bar a2, all of this divided by a1 plus a2. Okay, it's essentially the application of the formula from above. Okay, so that's essentially that situation there, and that is essentially that situation there that is used. Okay, so I don't want to decry that as much. Okay, but the general formula is this. So when we say that we have n simple connected shapes, so the general formula, looking at the general formula, so say we have I is equal to 1 to n simple connected shapes, each of area ai. Okay, and the general formula is then general formula is the area weighted average of the centroid of the individual bodies. Okay, area weighted average of the individual shapes. All right, so best way to understand this is by means of some examples. Okay, and this is what we're going to be doing. So the first example is of course going to be an L shape, second example is going to be a T cross section, and these same examples will be made use of in the next lecture for the moments of inertia as well. Okay, all right, so let's look at a couple of problems. Okay, so problem, in this problem I have the following cross section. Okay, with some dimensions and so on given to me. Okay, so given the cross section as follows. Okay, all right, so here is an L section, and I'm told that the thickness, let's say the dimensions here are given to us. So this is going to be 20 millimeters. Okay, this length here is going to be 100 millimeters. All right, this thickness here is going to be 20 millimeters as well, and the total height of this L-shaped cross section is going to be 100 millimeters. Okay, as drawn here. This is 100 millimeters as well. Okay, this is a fairly nice geometry here. There is not much of a problem for confusion, if you can see that. Okay, so this is the length along this side, and likewise this is the thickness of the cross section. Okay, what we need to do is locate the centroid of this shape. Okay, so locate the centroid of this shape. That is the problem that we need to solve. Fairly straightforward, as I said. The first step is divide this composite shape into the minimum number of simple connected shapes. Okay, so let's do this step by step. So here are the steps. So step 1, and this is the dimension that you can see here. Okay, so step 1 is divide this composite shape into a minimum number of simple connected shapes. Okay, this is always the key step. Okay, of course I can take any body and divide it into like millions of simple connected shapes, but I'm looking at the minimum number of simple connected shapes. That's the first step. Then the second step is choose a suitable origin and a coordinate frame. Choose a suitable origin and a coordinate frame, Cartesian coordinate frame, of course. Okay, I just want to make sure that the word origin is written properly here. These are all the key steps, and you'll see that these are fairly straightforward problems. So choose a suitable origin, okay, and a coordinate frame. This is your choice. Okay, and then the third step is apply the area weighted formula. Okay, the third step is locate the centroid of the simple shapes, connected shapes, with respect to the chosen origin. Okay, and then apply the area weighted formula, or the general formula. Okay, and so once again the key word here is that locate the centroid of the simple connected shapes with respect to the chosen origin. Okay, or with regards to the chosen origin, and then apply the area weighted formula. So these are the steps that you're going to be typically doing for each and every one of the centroid problems. So once again, divide the composite shape into a minimum number of simple connected shapes, choose a suitable origin and a coordinate frame, locate centroid of the simple connected shapes with respect to the chosen origin, and then apply the area weighted formula, or the general formula for these problems. Okay, so I'm going to copy my figure from here. Okay, I'm going to bring that creature down. Okay, so here is my L shape, so I'm going to copy that here. Okay, so, and let us look at the problem step by step here. Okay, if I bring that down here, so here is where I have brought it. So my first step is to divide it into a minimum number of simple connected shapes. So I can do the following. Let me do this. Okay, I can either do step 1 in the following, when I'm going to do it 2 times, just to show you that you can either do this or that. Okay, both of them are completely valid. Okay, so, and let me take this and scoot this down a little bit. Alright, so you can either do this or that. Okay, I can take this and break it into a simple shape in the following manner. So I can take that and say this is one thing. Okay, this is shape 1. And here is shape 2. Right, as you can quite clearly see. Okay, this is my first step. Or I can do the following. I can say that, okay, hey, this is going to be shape 1. Okay, that is also completely valid. I can take that and say, okay, hey, this creature is going to be shape 1 for me. Let me scoot this fellow down a little more so that you can see everything. Okay, and I can say that, okay, hey, this is going to be the other piece of this composite shape. Okay, this is the first step. Okay, so you can either do it this way, where you have this as one of your composite shapes, or I can have it in the following manner here. Okay, where this is the situation. Okay, both are completely fine. Okay, both ways of doing so are completely fine. Okay, of breaking into simple connected shapes, both ways of simple connected shapes. Is okay. Okay, so this is fine, that is also fine. I'm going to just choose one particular way of doing so, and then I'm going to go ahead with the solution for our problem. Okay, so here is our situation. So let me expand that a little more. I guess it's not letting me do it. Okay, so I just want to make sure that I'm expanding it with respect to, I don't want to rotate it, but I'm almost there. Okay, I really appreciate your patience when I do all these kinds of tricks on here. Okay, all right, so I'm going to break this into the following situation. Okay, so I'm going to break it into one shape that is going to be this one here, and as I said, you can do either ways. Okay, so this is shape 1. Okay, and then the other is shape 2 for me, which is a composite shape that is drawn here. Okay, and what I'm going to do after this is I'm going to set up an origin for this shape as the following. Okay, once again, this is not letting me draw straight lines, so I'm not sure what the deal is, but I don't want it to look like that. Okay, all right, so I'm almost there, pardon me. All right, fantastic. And then I set up an origin for this shape here. That's going to be the following. So I can say that, okay, hey, this is my y-axis. Once again, it's not letting me draw straight lines. So here is my y-axis, and then here is my x-axis. Okay, and so I'm going to label this as y, and then this is the x-axis, and then I'm going to locate the centroid of each of these simple shapes. Okay, so this is the centroid location of this shape here, and then obviously this is going to be the centroid location of this shape here, and then here is my origin. Okay, so this is my origin O. Let me write that here. So this is my origin O here. Okay, this I'm going to call as centroid C1 for my shape. Let's call this as C1. Okay, so this is centroid C1. This is centroid C2. Okay, so this is going to be the area A1. This is going to be the area A2. Okay, and then I'm going to write down the locations of these centroids from the origin O. Okay, so first of all, I'm going to have the location of C2. So I'm going to do that first. Okay, so starting from the origin, this height here is going to be the following. This height I'm going to decide and call it as y1 or y2 bar. Okay, this is y2 bar. Then I'm going to call this height here the location of this centroid with respect to the origin here. Okay, and that's going to be a height y1 bar. Okay, once again I want to draw that clearly. Okay, so this is going to be, well, doesn't let me draw straight lines for some reason. Okay, I don't know why. Just want to cut that out, and then read right here. Okay, so this is not very, this is quite frustrating. I apologize. It's still not letting me do it for some reason. Let me try a different location. All right, we're almost there. Okay, so I'm just going to do it this way. Okay, I'm just going to call it as y1 bar here. Okay, likewise I'm going to have x1 bar and x2 bar. Okay, look at this. So starting from the origin and then all the way from the center of this particular shape, I guess my nemesis of the straight line is still reckoning to me. This distance here is going to be called as x1 bar. Okay, and then the location all the way from the origin to where the centroid of C2 is sitting is, I'm going to call that as x2 bar. Okay, so that's going to be x2 bar. All right, and previously we had some of these dimensions that were given to us. So if I look at the dimensions that were given to us, okay, we have them as the following. So starting from here, and if I look at the total height of this creature here, that was 100 minus 20, because the thickness was 20, so this is going to be 80 millimeters, and the thickness of this piece here was around 20 millimeters, if I was right. Okay, this was 20 mm, and likewise this height here was 20 millimeters. Okay, this was 20 millimeters, and the total length starting from where the origin is all the way to where the piece ended here, that was 100 millimeters. Okay, so that's something that will be useful for us in deciding what these distances x1 bar, x2 bar, and so on are. Okay, so this was 100 millimeters, and so by looking at the figure you can immediately see that okay, x1 bar is going to be half of 20, x2 bar is going to be half of 100, and then y1 bar likely is going to be half of the 80 millimeters plus a 20 millimeter distance that is added, and then y2 bar is going to be half of the 20 millimeter distance. Okay, so if I write everything down, so I just collect all my values, I'm going to say that okay, for shape 1, okay, I'm going to have A1 is you see the area of the first shape is going to be 80 by 20. Okay, so this is going to be 80 mm multiplied by 20 mm. Okay, and then x1 bar is going to be half of 20, so that's going to be 10 millimeters, and y1 bar from the origin that we have chosen is going to be 20 millimeters plus half of that height here. So this height, if I mark it out, is going to be 40 millimeters. This is these are all simple problems, but then the chances of making a mistake are pretty steep. Okay, so this is going to be 40 millimeters. Okay, it's going to be 40 plus 20 or 60 millimeters. Okay, so y1 bar is going to be 60 millimeters, and then likewise I'm going to have A2, which is the area of the second piece, that's going to be 100 by 20. Okay, so that's going to be 100 mm by 20 mm, and then x2 bar is going to be, as you can see, half of 100 millimeters, which is going to be 50 millimeters. Okay, so this is going to be 50 millimeters, and y2 bar is going to be half of the 20 millimeters, which is 10 millimeters. And as is our want, we will be marking these distances by means of dotted lines. Okay, just so that we are aware that these are distances that we are marking. Likewise here as well. Okay, and so on here too. All right, and we're almost there. All we have to do is make use of the formula that we have obtained from the previous step. Okay, so by making use of the formula, we just have the following. So x bar is going to be x1 bar a1, x2 bar a2 divided by a1 plus a2, and then y bar is going to be y1 bar a1, y2 bar a2, this is x2, divided by a1 plus a2, and this is the centroid location of the composite shape. Okay, if I do the substitutions, I get the following. Okay, so x1 bar or x bar is going to be x1 bar, which was 10 millimeters. Okay, right, so this is 10 times. The area was for a1 was 80 times 20. Okay, plus x2 bar, which was 50, right? So that's 50 times 100 times 20. Okay, and all of this is going to be divided by 100 times 20 plus 80 times 20, and if you do the calculations, you obtain x bar is going to be 32.2 millimeters. Okay, and then likewise y bar is going to be y1 bar, which was 60, okay, times the area, which was 80 times 20, plus y2 bar, which was 10 times 100 times 20 divided by 100 times 20 plus 80 times 20, and this gives you y bar, is also equal to 32.2 mm. Okay, and these are the calculations that result in the following answers. And one way of doing this is, okay, if I can take this figure from before, okay, if I copy this, I can actually locate the presence of x bar and y bar for the entire shape as the following. Okay, so we can say that if this is the situation, I don't want to tilt it, of course. Okay, so with respect to x bar and y bar, we found out that with respect to x and y, we found out that x bar is 32.2 mm, and then y bar is also 32.2 millimeters, which means that with respect to the origin O, here is perhaps y bar. Okay, so maybe let me clean up the figure from some of these things. If I can cut these off. Okay, let me draw that out here. Let me get rid of these things as well. Okay, and then let me say that, okay, where is the location of the centroid? The location of the centroid of the composite body is probably somewhere here. It's going to be a little between x1 bar and x2 bar, and then between y1 bar and y2 bar. So in my case, the centroid of the entire body is sitting somewhere here, and so this is the distance that I'm going to be marking. Okay, so starting from there, I have this distance all the way to the origin here. Okay, that's going to be y bar for me. Okay, so that's y bar, which is 32.2 mm, and then I'm also going to be having x bar, okay, all the way from here, which is the origin line. Okay, and I guess I should be drawing this a little better. Okay, all the way from here all to there is going to be my x bar. Okay, and so this is going to be x bar, which is also 32.2 mm. All right, so this is an example, and you can call this centroid as centroid C, which is x bar and y bar, and this is the value that you have for x bar and y bar with respect to the origin that you have chosen here. Okay, And I want to solve one more problem. I appreciate your patience in sitting through my lectures. I know that we go a little beyond time, but I want to compute these problems so that this is useful for you later on when you look at strength of materials. Okay, so you can actually in some sense skip the early parts of the lectures and then directly go to these problems if you want. Okay, all right, so I'm going to move on to the next problem. This will be a short problem as well, as you'll see. Okay, in this problem we have a T section. Okay, so the T section is drawn as follows. So here is the T section, and we will take a lot of liberties with this particular problem in terms of doing it quickly, because now we know what we can do, right? So the T section has the following geometry. Once again, dimensions are given to us in millimeters. Okay, so I'm just going to write the dimension here. The thickness of the top flange is going to be 20 millimeters. Okay, and the thickness, the width of the top flange is going to be 100 millimeters. Okay, the thickness of the middle section is going to be 20 millimeters, and the height of the middle section all the way from here onto there. Okay, this height is going to be 80 millimeters for us. Okay, so this height is 80 millimeters, and what do we need to do? We need to locate the centroid. Okay, locate the of this T section. The previous problem was an L section, right? So this was an L section. Okay, and in this problem this is a T section. So the first step is of course break it into simple connected shape. So I'm going to copy the steps from before. Okay, here are the steps that we had made use of. So the first step is divide the problem into simple connected shapes, then choose a suitable origin, and then locate the centroid of the simple connected shapes with respect to this origin, and then all you have to do is apply the general formula. Okay, so these are the steps that we're going to be making use of in this problem as well. Okay, so I just want to make that note here. Okay, so divide the composite shape into a minimum number of simple connected shapes. In this case we're going to be dividing this into 2. Okay, so for the T section, I is equal to 1 and 2. Okay, 2 simple shapes. That's for the T section that you can see there. Then we choose a suitable origin and a coordinate frame, and then we just go on our simple way that calculate the locations and then use the formula. Okay, so let me do that right now. I'm going to copy this picture. Okay, and I'm going to just choose a suitable origin, and then I'm going to be on my way. Okay, so here is the situation. Okay, I'm going to get rid of some of these, cut these off, and then cancel these off, and I can choose whatever is the origin for me. Okay, so here is what I'm going to be doing. I'm going to be choosing this cornermost point here as my origin O, and watch this. Okay, I'm going to be setting up my coordinate frame starting from here all the way down to here is going to be my coordinate frame for X, and then you see starting from here all the way down here is going to be my coordinate frame for Y. Okay, of course this is going to be vertical. Okay, so this is going to be positive Y. So positive Y is actually down for me. Okay, unlike in the previous situation. Okay, now what are my simple shapes? It's fairly obvious to see that okay, one of them is going to be this top flange here is the first simple shape that I can draw. Okay, then the second simple shape is going to be this middle piece here, the height section. Apologies. Once again, I'm facing my old nemesis, which is drawing straight lines. So for some reason I'm unable to do that properly, at least in this particular lecture. So let me do this very, very slowly. Okay, even then it's not letting me do it. Well, nevertheless, let's say that this is what we end up with. Okay, apologies. If you have a secret for drawing these straight lines, then please do let me know. Okay, All right, so this is going to be shape 1 for me, and then this is going to be shape 2 for me. So I'm going to call this as area A1. Okay, this is going to be area A1, and then this is going to be area A2. And if you look at the dimensions, you know that this dimension is going to be 20 millimeters, right? The thickness is 20 millimeters. This thickness is also 20 millimeters. The total height is 80, and the total length of the flange is 100 millimeters. So you can mark that distance right here if you want. Okay, this width is going to be 100 millimeters. Okay, and then the total height from all the way from here onto there, if I draw that out. Well, this time I'm successful in drawing the these straight lines. Okay, this is 80 millimeters. Okay, these are the dimensions that we will be making use of. Then what I have to do is I have to set up the origin for this centroid, this composite simple shape. That's the centroid for that simple shape, and then for this simple shape, here is the centroid for this simple shape. Okay, and here is what I'm going to do. Okay, starting from the origin, I have to locate the x location of the centroids. Now you see that this is fairly straightforward. Okay, if I look at using a dark color for this, so starting from here, you see that the centroid of both of these bodies are coincident. Okay, so by means of symmetry, you can automatically say that the location of x1 bar is the same as the location of x2 bar is the same as the location of x bar. But I'll prove that by means of actually doing the problem. Okay, so this is going to be x1 bar, which is the same as doing x2 bar. Okay, then I have to do y1 bar and y2 bar. So here is where I start off with, right? Then I go all the way down here. That's my y1 bar. Okay, and then all the way starting from here to where the other centroid is going to be y2 bar. Okay, this entire length here is going to be y2 bar. Okay, so things that you can see, and of course if I shade this out, this is one of my composite shapes, and then the other one is going to be this creature here. Okay, and this is you can call this as C1. Okay, this is C1, and then this is C2. And by symmetry, you can make the argument that x bar is the same as x1 bar is equal to x2 bar. We can do that, okay, by symmetry. X1 bar is equal to x2 bar is equal to x bar. Can also obtain this by means of the formula. Okay, then we will first of all collect all these areas and so on. Okay, so area A1 is going to be 100 by 20, area A2 is going to be 80 by 20. Okay, so let me write that out. Okay, so area A1 is 100 mm by 20 mm. Then x1 bar, as you can see from the figure here, is going to be half of 100, which is going to be 50 mm. Okay, so this is going to be 50 mm, and then y1 bar is going to be half of 20, which is 10 mm. Then x2 bar is going to be let me do the second one. So x2 bar in this case is also going to be 50 mm, but before that let me write the area A2. Okay, area A2 is going to be 80 mm by 20 mm, so many millimeters square. X2 bar, as you can see from above, is going to be the same as x1 bar, so that's going to be 50 mm as well. And then y2 bar is going to be the following. Okay, it's going to be half of 80, which is 40, plus the height 20. Okay, so it's going to be this height, which is going to be 40 millimeters, right, as you can see, and then plus 20 millimeters, so that's going to be 60 millimeters. Okay, 60 millimeters, and then we make use of the formula. Okay, then x bar is going to be x1 bar A1 x2 bar a2, all of that divided by a1 plus a2. And if I do the substitutions, this is going to be 50 times 100 times 20, 50 times 80 times 20. It's quite obvious to see that the answer will also end up being 50. Okay, this is multiplied by 100 times 20, 80 times 20. Okay, this will end up being 50 millimeters, and so x bar is 50 mm. Can also obtain by symmetry. Okay, then I have y bar is going to be by the formula y1 bar a1, y2 bar a2, all of this divided by a1 plus a2, which is going to be y1 bar, which you can see is 10 millimeters. So this is going to be 10 times the area, 100 times 20. Then y2 bar is 60 times the area, which is 80 times 20. All of this divided by 100 times 20, 80 times 20. And this gives me, surprise, 32.2 millimeters. And so this is y bar is equal to 32.2 mm. Okay, and then if you want to locate the centroid of the entire body, here is the idea. Okay, so typically this is something that I expect you to do in the exams as well. Okay, so I'm going to take this entire shape. Okay, if you want, I'm going to copy that and I'm going to bring that here. Okay, and we said that okay, this shape here was the first simple connected shape. So I think I drew this in the blue color, right? This was the first simple connected shape, and then the other shape was this creature here. Now I come to my nemesis, which is the drawing of the straight lines. So I think I can do the following. So that's not bad. Should have probably done the same thing in the previous figure as well. So then I had my origin, which was set up here. That is very, very important. This was my origin O. Okay, and based on that, this was the this was the positive y direction, right? This was the positive y direction, and then this was my positive x direction. That is very, very important. And then for each of these creatures, I'm going to set up the centroid. So for the centroid of the first piece, here was the centroid, right? Then I had the centroid of the second piece, which was right in the middle somewhere here, right? And then I have the centroid of the main body, which is sitting somewhere here. Okay, so this is going to be centroid C1, this is centroid C2, and then this is the centroid of the entire body, which is the location C. Okay, and if I write out from here, this location is going to be let me take this creature and then draw it here. This is the y-axis, and here is the centroid of the main body itself, and this is going to be y bar, which was 32.2 mm. And then of course we have the location of x bar, which is the same as what we have for each of the other bodies as well, as you have seen. And this is the location x bar. Okay, this is x bar, and then x bar is 50 mm and y bar is 32.2 mm. And just in summary, the main steps to locate the centroid are the following. Okay, so main steps: to locate the centroid of composite shapes. Okay, I'm just going to copy the steps that I had written down here for the previous problem. Okay, and then I'm going to bring that down once again here. You can divide it into any type of a composite shape. I mean, I can, as I showed in the L section, you can either do it this way or the other way, right? And likewise for the T section. T section is fairly more straightforward. You can just see two rectangular pieces. Okay, so the basic idea is I have to divide the composite shape into a minimum number of simple connected shapes. Okay, this essentially tells me, okay, what is I is equal to 1, 2, 3, all the way up to n. Okay, and then I say that, okay, I choose a suitable origin and a coordinate frame, and then locate the centroid of the simple connected shapes with respect to that, and then apply the area weighted formula, which is the general formula, and the general formula is the following. Okay, right, just to reiterate, I can have x bar is equal to summation I going from 1 to n xi bar ai, all of this divided by summation I is equal to 1 to n ai, the area weighted average. I can have I going from 1, 2, 3, 4, depending on what the shape is. Okay, we need not be restricted to just two simple connected shapes. Okay, and then y bar is going to be likewise summation I is equal to 1 to n yi bar ai, all of this divided by summation I is equal to 1 to n ai. Okay, this is the general formula where xi bar yi bar is the location of the centroid of the ith simple shape of area ai with respect to the chosen origin of a suitably drawn coordinate frame. Okay, and then obviously x bar y bar is the centroid of the composite shape. Okay, x bar and y bar is the centroid of the composite shape. All right, and so this is the general formula. Okay, and once again, the basic steps: divide the the composite shape. So the basic steps are: divide the composite shape into a minimum number of simple connected shapes, choose a suitable origin and coordinate frame, locate the centroid of the simple connected shapes with respect to the chosen origin, then apply the area weighted formula or the general formula that is written down here, and the key is divide the composite shape into a minimum number of simple connected shapes. Okay, that is very important to understand. Otherwise you're going to end up having more simple connected shapes. I mean, you'll still get the right answer, but it's just going to be more painful. And here is the general formula: x bar and y bar is the centroid of the composite shape. Let me just write this again. Okay, for some reason my handwriting is pretty much askew today. Centroid of the composite shape, and then x bar I and y bar I is a location of the centroid of the ith simple connected shape of area ai, and this is with respect to the chosen origin of a suitable coordinate frame. All right, I hope you're all staying safe out there. We're almost at the end of the semester. I wish you all the best. We will be having one more lecture, and then I'll plan on having a review session where I'll solve some problems and post it on Carmen. Okay. So in the next class, we will be looking at the idea of moment of inertia. We will be looking at the same shapes, the L shape and the T shape. Okay, and then we will be continuing forward. Okay. All right. Thank you very much.